Hello dear students, welcome back. So today we are going to start a new video for haloalkane and haloarene. So in this video we will study the mechanism. There are two different types of substitution nucleophilic reaction mechanism. They are Sn1 and Sn2. Sn1 means substitution nucleophilic unimolecular and Sn2 is substitution nucleophilic bimolecular. So we'll study these two mechanisms in details. So we'll start with Sn2, substitution nucleophilic bimolecular. Now in this mechanism, there is only one step. It's a single step mechanism. So in this mechanism, we take a haloalkane and we consider the three-dimensional representation of haloalkane. So this is a three-dimensional representation of haloalkane. This is a primary haloalkane. Now here, this bond is wedged bond. This is dash. Now these two are on the plane. This is above the plane and this is below the plane. Or if you consider an observer, say I am the observer, this bond will be facing toward the observer, whereas the this bond will be away from the observer. So this is a three-dimensional representation of haloalkane. A nucleophile, since it is a substitution nucleophilic reaction, one nucleophile is replaced by another nucleophile. So in Sn2 mechanism, the incoming nucleophile will attack the partially positive carbon. Now, why partially positive? Because in CCl bond, Cl is more electronegative than C. That means chlorine is more electronegative than carbon. So chlorine will be partially negative because the electron density will be shifted toward chlorine and carbon will be partially positive. So the incoming nucleophile, that is OH negative, will attack the partially positive carbon from an angle of 180 degree to CCl bond. Now why 180 degree? Because if the nucleophile attacks the partially positive carbon from 180 degree, the steric hindrance is minimal and also the repulsion between the nucleophile is minimal. So when the incoming nucleophile attacks the partially positive carbon from an angle of 180 degree, it forms a transition state. This is the transition state where CCl bond breaking will take place and COH bond formation will take place. That means in transition state, both bond breaking and bond formation will take place. Now this transition state is highly unstable because of the pentavalent nature of carbon. So this will decompose to give the product. This is the product form. Now you can see the difference. In the reactant, the nucleophile is on the right hand side, whereas in the product, the nucleophile is on left hand side. So there is an inversion in the position of nucleophile. So this inversion is known as Walden inversion. So in Sn2 mechanism, we get inverse product. Now, when it comes to the reactivity order of different types of haloalkane, the tertiary haloalkane are least reactive, whereas primary haloalkane is most reactive. Let us see with the help of the structural formula. This is primary, 1 degree haloalkane. Secondary will have 2 alkyl groups to the carbon having halogen atom, and tertiary will have 3 alkyl groups. Now, Sn2 involves backside attack of nucleophile to the partially positive carbon. Now, here you have 1 alkyl group, here you have 2, and here you have 3 alkyl group. So when it comes to the backside attack, the steric hindrance will be maximum here, and steric hindrance will be minimum here. That is, 1 degree will have minimum steric hindrance, and 3 degree will have maximum steric hindrance. Now, since Sn2 involves backside attack of nucleophile, the steric hindrance plays a very important role in deciding the reactivity order. So, since primary has minimum steric hindrance, will have maximum reactivity. So 1 degree haloalkane will be more reactive than 2 degree haloalkane, and 2 degree haloalkane will be more reactive than 3 degree haloalkane. Next, let us see Sn1 mechanism. Sn1 is substitution nucleophilic unimolecular. Now, in case of Sn1, there are 2 steps involved. Step 1 is formation of carbocation. For Sn1, we'll consider 3 degree haloalkane. So this is 3 degree haloalkane. So in the first step, the C-Cl bond in haloalkane will undergo heterolytic cleavage. Now there are 2 types of cleavage, homolytic and heterolytic. Homolytic means the bond breaking which involves equal distribution of electrons, whereas heterolytic involves unequal distribution of electrons. So the C-Cl bond will undergo heterolytic cleavage. That means heterolytic bond breaking. So if this C-Cl bond breaks, Cl will get the electron because Cl is more electronegative than carbon. So we'll get Cl negative, and carbon will attain positive charge. So you can see there is a carbon compound carrying positive charge on carbon. So this is carbocation. Step 2 is nucleophilic atom. So in this step, the incoming nucleophile will attack the positively charged carbon. This incoming nucleophile will attack the partially positive carbon to form product. Now here, in this mechanism, there are two steps. Step 1 involves breaking of bond. So this step is the slow step, whereas the second step involves formation of bond, that is OH will attack, which is nucleophile, will attack the positively charged carbon to form the product. So this is fast. Now we know the rate of a reaction is always determined from the slow step. So for this reaction, the rate will be rate constant, concentration of haloalkane Rx. Now, for Sn1 mechanism, the rate is only dependent on the concentration of haloalkane. That means only one molecule is involved. That's why it's known as unimolecular. Whereas, if you look at the Sn2 mechanism, you'll find initially, that means starting the mechanism, it involves two molecules. That's why it's known as bimolecular. Now let us see the reactivity order of different types of haloalkane, that is primary, secondary and tertiary. Remember this point, Sn1 involves formation of carbocation. So this is primary haloalkane. Secondary haloalkane, and this is tertiary haloalkane. So Sn1 mechanism involves formation of carbocation. If we take primary haloalkane, you'll get 1 degree carbocation from here. If you take secondary haloalkane, you'll get 2 degree carbocation. And if you take tertiary haloalkane, you'll get 3 degree carbocation. Now if you compare the stability of carbocation, 3 degree carbocation is more stable than 2 degree carbocation. And 2 degree carbocation is more stable than 1 degree carbocation. So the stability order is 1 degree carbocation less stable than 2 degree carbocation is less stable than 3 degree carbocation. So if we look at this stability order, you'll find 3 degree haloalkane will be most reactive toward Sn1 mechanism, and 1 degree will be least reactive toward Sn1 mechanism. So what is the order? 1 degree less than 2 degree less than 3 degree. So you will find in case of Sn2 the order is 3 degree less than 2 degree less than 1 degree, but in case of Sn1 1 degree less than 2 degree less than 3 degrees opposite. Next, let us see the reaction of haloalkane with matter. reaction with sodium metal. Now, haloalkane reacts with sodium metal in dry ether medium to form an alkane. With twice the number of carbon atom present in alkane. Now, say if you start with one carbon alkyl group, you will get an alkane with 2 carbon. If you start with 2 carbon alkyl group, you will get an alkane with 4 carbon. And this reaction is known as Wood's reaction. An example, C2H5Cr. The name of this compound is chloroethane. If chloroethane reacts with sodium in dry ether medium to give butane, and the side product will be 2 molecules of sodium chloride. Next, let us see the reaction of alkyl halide with magnesium metal. If alkyl halide reacts with magnesium, it forms a compound with molecular formula RMgX, and this compound is known as Grignard reagent. This is a very useful compound in organic chemistry. Many compounds can be synthesized from this reagent. Next, let us study elimination reaction. This elimination reaction is also known as dehydrohalogenation reaction, where D stands for removal. So in this reaction, we'll remove hydrogen and halogen from a haloalkane, and the product we get is alkene. Let us take an example. CH3, CH2, Cr. Now, the reagent will tell you whether this is an elimination reaction or not. So if you see this reagent, KOH, potassium hydroxide, in alcoholic medium. So if you see potassium hydroxide in alcoholic medium, the reaction will be elimination reaction. So what do we do here in this reaction? We remove the halogen first. So this is the halogen which we are going to remove. Now the halogen is removed from this carbon. So this carbon is alpha carbon. So the carbon next to alpha carbon is beta carbon. So if you remove the halogen from alpha carbon, the hydrogen, it has to be from beta carbon. That's why this reaction is also known as beta elimination reaction. So if you remove Cl from here, you have CH2. One hydrogen from here, also CH2, and there will be a double bond here. The name of this compound is ethene. Let us take one more example. So this is 2-degree haloalkane. and name of this haloalkane is 2-chlorobutane. Now in case of 2-degree haloalkane, you have 2 beta carbon. So this carbon has chlorine atom, so this is alpha, this is beta, this is also beta. So now you have 2 beta carbons in this haloalkane, so we'll give 2 products. Now if we take hydrogen from here, the product form is CH3, CH2, CH double bond, CH2. But if we take the hydrogen from this carbon, the product form will be CH3, CH double bond, CH, CH3. This is but 1 in, this is but 2 in. Now here, one of the product will be major product and the other one will be minor product. Now the major and minor is decided by a rule which is known as Sedgwick rule. Now according to Sedgwick rule, the alkene with more number of substituent will be the major product. Now substituent means the alkyl group. So it's a very easy way to find the major product. Now these 2 carbon, they have double bond between them. Now if you look at the carbon on the right hand side, you don't see any alkyl group here. And the carbon on the left hand side has got 1 alkyl group, that is ethyl. In the second compound, these 2 carbons, that is carbon 2 and carbon 3, they have double bond between them. This carbon has 1 alkyl group, this carbon also has 1 alkyl group. So the total number of alkyl substituent in but 2 in is 2, whereas in but 1 in you have only 1 alkyl substituent. So if we compare, here you have 2 alkyl substituent, here you have only 1 alkyl substituent. So this will be minor, this will be major, according to Sedgwick rule. Next, let us see the reactivity difference between haloarene and haloalkane. So we find that haloarene is less reactive than haloalkane toward nucleophilic substitution reaction. So there are different factors. The most important factor is resonance. Then we have difference in hybridization, then planarity, okay? So the important factor for the reactivity of haloarene less than haloalkane is resonance. Resonance is basically the delocalization of pi electron. So let us take a haloarene, let it be chlorobenzene. So this is chlorobenzene. Chlorine atom has got 3 pairs of free electrons. So the resonance will start from here. This free electron will go and form bond between chlorine and carbon 1. This bond will break, electron will go to carbon 2. So the next resonating structure. So this pi electron will undergo delocalization to give more number of resonating structures. Now, you can see from the resonance, there is a double bond character generated between carbon and chlorine. which is not seen in the case of haloalkane. Haloalkane, it will not show the property of resonance. So haloarene, because of resonance, gets double bond character between carbon and chlorine, and this double bond is difficult to break compared to single bond in haloalkane. So if you compare, where is it easier to substitute the nucleophile? It's easier to substitute the nucleophile in haloalkane. Why? Because the CCl bond is weaker in haloalkane compared to haloarene. That is the important factor which decides the reactivity of haloarene and haloalkane toward nucleophilic substitution reaction. Next, let us see some important electrophilic substitution reaction for haloarene. So in order to understand this electrophilic substitution reaction for haloarene, first let us see the resonance. Now, due to resonance in haloarene, carbon 2 is negatively charged, carbon 4 is negatively charged, and carbon 6 is negatively charged. So the incoming electrophile, since electrophile is an electron deficient species, will prefer to attack carbon 2, 4 and 6 instead of carbon 3 and 5. So carbon 2 and carbon 6 represents ortho position, whereas carbon 4 is para position. 3 and 5 is known as meta. So the electrophiles are ortho and para directive if we have a halogen atom present here. So we'll see the different types of electrophilic substitution reaction. Thank you so much.